Okay, so we have a lot to cover today because next class is our second exam. So next Monday is our exam. It's going to cover chapters 9, 12, 15, 16, and 18. Everything that we've done since the first exam. So that includes interest rate risk, value at risk and expected shortfall, and then the Basel Accords. The exam 1 makeup is due Friday. So make sure you get those in if you want to improve your exam 1 grade. And just so that we're all clear about how the exam is going to work, the exam is going to be pen and paper, same as last time. You can bring a formula sheet, front and back, and you can write whatever you want on that sheet. You can also bring a calculator, but no other resources. So before I start the review, does anyone have any questions about the exam that's going to be on Monday? Okay. So let's start by reviewing some important concepts. Starting with chapter 9. The first thing we talked about was the management of net income interest. It's possible you'll see a question like this on the exam where you take a look at a bank's deposits and the loans that they provide. And what will happen is that due to liquidity preference theory, investors will prefer to invest for a shorter period of time if the interest rates are the same. And so typically longer maturities correspond to higher rates of return. An example question could be, what are the bank's losses if interest rates in 2 years go up by 1%? Well, the deposits after 2 years will have the new rate, but the old mortgages will be stuck at that lower rate. And so there will be a loss for the bank. Liquidity is the concept of being able to exchange your assets for their full value. If something is illiquid, it means it is hard to convert it into cash that can be used to pay off debts. And this becomes a problem for banks that pay off short-term deposits with long-term mortgages. We also know that there are liquidity requirements in Basel III. So definitely look out for that. We then discussed different types of rates and what they mean. Treasury rates are rates set by the U.S. Well, they're not set by the U.S. governments, but they're on U.S. debt. And they are presumed to be risk-free. So you usually have a pretty low rate of return, but it is guaranteed. While LIBOR is a London interbank offered rate, it is a higher rate that represents loaning between AAA rated banks or AA rated banks. We also discussed forward rates. And I do want you to be familiar with how to calculate forward rates. The idea being that a forward rate moves you from one spot in time to a future spot in time. Instead of thinking of being at time 0, you can have a forward rate starting at time 3 that applies from time 3 to time 4, as an example. There's a lot of details here talking about how to calculate forward rates. Another type of interest rate is the OIS rate, or the overnight index swap rate. The difference between this and LIBOR is that the OIS applies only to interest, while LIBOR applies to interest and principal. And so the credit risk with LIBOR is much more than the credit risk with OIS. Therefore, we use OIS to determine a sort of the difference between the OIS rate and the LIBOR rate can tell us how confident banks are feeling in the market, because it has a reduced credit risk. And so some analysts use this spread between LIBOR and OIS to denote when there are market stresses. And here we see the financial crisis of 2007-2008 had a big impact on the LIBOR OIS spread, because banks became less willing to lend it to each other. They required a higher return, because the LIBOR rate is based off of the entire principal. Okay, any questions about those interest rates? Question here. Sorry, what was that?
Yeah.
Oh, is it not on Canvas?
Yeah.
Let me fix that real quick. Let me get this on Canvas. That's weird. I did not upload this. Okay, I just uploaded that PowerPoint onto Canvas. So I'll give a minute for everyone to open that up and download it. All right. So one of the things to note about these interest rates is that you can use them to denote when there is market stress. Next concept I want to go over is the idea of duration, which tells us the sort of time value of our portfolio, an average time value. We use duration to find the percent change in our portfolio value while the rates change. And so these two different interpretations give us different ideas about how duration works. One way is to think about it as the proportional change. And one way is to think about it as a weighted average of time. The reason why this works is because when you take the derivative of the present value of a cash flow in terms of the interest rate, you're going to have a t term out in front. And then that t term is weighted by the proportion of the present value attributed to that cash flow. One thing to note about duration is that in the formula for duration, they include a negative sign out in front. That makes most instruments have a positive duration. So let's look at an example. You might be given a table like this and asked to compute the duration. Well, you'll be given a table that might look just like this part. Oops. You might only have the first two columns, and then you'd have to figure out everything else. So what is done in this table is a present value is found, That present value is divided by the total present value to get a weight. And then the weight and the time is multiplied together to get us that weighted average. Then you add all those terms up to get the duration. So the duration of this bond is 2.65. This should sort of make sense because most of the payment occurs at time 3. So the duration is going to be close to 3. The other cash flows reduce the duration a little bit, but not by much, because they're a small amount of the total weight. We then discussed the idea of modified duration, which is an adjustment you have to make when you don't have continuous compounding. So if you have annual compounding, then this derivative operation and the weighted sum explanation aren't exactly equal. So an adjustment term of 1 plus the yield is added in order to make it so that they have the same representation. So that 1 point y, 1 plus the yield, allows us to take the derivative and have it be the same weighted sum as with the Macaulay duration. Yes.
So previous patient, let's say we want the modified the one that we did.
The Macaulay, yeah, the original duration is the Macaulay duration. And this has to do with continuous compounding. That's when you just take the derivative divided by b and add a negative sign. The modified duration is when you have annual compounding or any other sort of non-continuous compounding. And so in those forms, you have a 1 plus I raised to the t. You need a 1 plus I term to cancel out with the derivative. Okay, the next type of duration we talked about was dollar duration, which is when you convert the duration into an absolute amount. So duration tells us the percent change in our portfolio because we took a derivative and divided it by b. If we don't divide by b, then we get the absolute change, which can be of more interest if you want to know how much your portfolio value is changing. And this idea is very similar to the idea of rho that we had from the Greeks, where we took the derivative in terms of the interest rate. The next idea to address is convexity. And we talked about the convexity adjustment that was needed in the fundamental review of the trading book. Here, a convexity adjustment or convexity term describes the second derivative of our portfolio value with respect to the yield. And we use the convexity component to improve our approximation. You can use a linear approximation to estimate the change in portfolio value by multiplying negative d times the change in the yield. But if you want a more precise estimate, you'll have to include the convexity adjustment, which is a second degree term. So it has a 1/2 coefficient in front and the change in y squared. This is just based off of Taylor series. And so you can expect to see a question that asks you to approximate the change in value of a instrument using using the duration convexity approximation. All right. So those are the main ideas from chapter 9, knowing the different types of interest rates, and then knowing how to calculate durations and convexities, things like that. So I definitely would recommend that you take a look at those problems. The next section that I want to look at is value at risk and expected shortfall. This section has a lot of calculations, and there's a lot of buildup that leads to the Basel Accords. So, value at risk is a risk measure that says we are X% certain that we will not lose more than V dollars in time T. We can express this in mathematical notation by saying the probability that your loss is less than V equals X. So as a picture, this gives us a percentile of our loss distribution. And we will often assume a certain type of distribution for our losses, either normal or perhaps uniform, so that we can calculate these values. So let's talk about example 1. Suppose that the gain from a portfolio during 6 months is normally distributed with a mean of 2 million and a standard deviation of 10 million. From the properties of the normal distribution, the 1 percentile point of this distribution is 2 minus 2.326 times 10, or negative 21.3 million. The value at risk for this portfolio with a time horizon of 6 months and confidence level of 99% is therefore 21.3 million. This was found, the value at risk was found by doing mu plus sigma and inverse of 1 minus alpha. So we have the mean, then we subtract off 2.3 standard deviations to get our final answer of negative 21 million. The thing that I want you to be on the lookout for is whether this model is for the gain or loss. Because if it's modeling losses, then you need a negative sign in front of the mu. And if not, then there should be, if it models gain, then there should be a positive sign in front of the mu. So make sure you keep that in mind. And another example that I could give is using the uniform distribution. So let's say that your losses are between 50 million and negative 50 million. So you have possibilities of losing $50 million and getting $50 million. And assume that the probability of each loss is uniform. That means that our PDF is rectangular. And it's easy enough to find areas with this. They're just proportional to the x's. So the 1% or the 99% value at risk represents the 99 percentile of this distribution, or the 1 percentile of this distribution, because we're looking at gains and losses, which occurs at negative 49 million. So our value at risk is 49 million. We then discussed another risk measure called expected shortfall. which uses value at risk in its calculations. It says, what are the expected losses given we're at our value at risk point or higher? So the expected shortfall can be expressed as the expected value of our losses given our losses exceed the value at risk. This type of risk measure is nice theoretically because it has certain properties that we call coherent. So a risk measure needs these 4 properties in order to be a coherent risk measure. Value at risk is not coherent, while expected shortfall is coherent. The 4 properties are monotonicity, translation invariance, homogeneity, and subadditivity. I want you to know what those 4 points are, with the most important one being number 4. So the first part, the fourth part, the subadditivity, is the important one because this is what breaks down for value at risk. Value at risk contains the other 3 components of a coherent risk measure, but not subadditivity. This example here shows you how subadditivity can be broken. It's when there are big tails beyond the value at risk. And so you can read this example to see that the value at risk for an individual asset can be pretty low, but when you add 2 assets together, their value at risk can balloon up if you have these large tails. On the other hand, expected shortfall will always satisfy subadditivity because it is a kind of average. And so because it accounts for everything that happens after the value at risk, expected shortfall will satisfy this condition. In the previous example, the value at risk was 1 for both investments, but here the expected shortfall accounts for the change or the big tail, and so the value at risk is 8.2. Much more representative of what you'd actually expect to lose if you were at this point. All right, there were 2 components to our risk measures that we really care about. The first one is the time horizon, and the second one is the confidence level. So the time horizon is important. As we saw with the Basel Accords, different instruments had different liquidity horizons that had to be accounted for. And the big thing that distinguishes a T-day value at risk from a 1-day value at risk is the square root of T term. What I want you to know about this is that this assumes returns are independent, which may or may not be a good assumption. For example, if you're looking at a stock and you look at the returns every day, you can do some tests to determine if the returns are independent or if they're related to each other in some way. One way to check this is to use what's called an autocorrelation. An autocorrelation is the correlation of a series with a lagged version of itself. In other words, you are comparing today's observation to yesterday's observation to see if they are related in any way. we have a couple of examples of how this could show up. You could have a positive autocorrelation, which is in the world of stocks is called a rally, or sometimes called a bull rally, where it goes up a lot. While you have a negative autocorrelation for something that exhibits reversion to the mean. So when there's an autocorrelation, that means that there is not independence. The variables are related or dependent on each other. In this equation here, this is just saying this is the variance of x plus y, or I should say x1 plus x2 equals the variance of x1 plus the variance of x2 plus 2 times their covariance. Which is rho sigma squared. Assuming that they have the same distribution. So this p looking character is actually rho. And that is the correlation coefficient, which is the same thing as the autocorrelation. So this gets applied. We want to consider looking at a t-day value at risk where the losses are correlated. If you have a loss one day, that might lead to more losses the next day, and so on. Then you'd have to use this formula to find what the standard deviation is. So this formula, the standard deviation of the t-day change in the portfolio is given by this value, which you would then need to multiply by a z-score in order to find your value at risk. Without an autocorrelation, or when rho is equal to 0, all this simplifies to just the square root of t, which is good, because that is what we expect. The next thing I discussed was calculating risk measures. So this is how you can take a 95% value at risk calculation and convert it to a 99% value at risk calculation. This is often easier to do in practice, to calculate a value at risk for a slightly lower confidence level and then translate that to a higher confidence level. Because it could be hard to calculate these things using raw data. The more data you have, the more accurate you can be about your assessment. And so you might have like 10 exceptions if you use a 90% confidence interval, but if you use a 99% confidence interval, you would only have one exception. It'd be hard to say, to make a lot of us inferences with only one observation. And another thing that you should know about this is that these value at risk or the expected shortfalls are with the same time horizon. So these two equations are things that I definitely would put down on my formula sheet, just because they're not things that I would want to memorize, but they are formulas that could actually be applied to a problem. Right? We then discussed back testing, which is trying to see if your assumptions about value at risk are accurate. And we do this by comparing the number of predicted exceptions to the number of actual exceptions. We can then run a hypothesis test where we assume that that the probability of an exception is actually this alpha percent. So what we can do is suppose that we are using a 95% confidence level, so a 95% value at risk. If we were looking at 100 days of data, we would expect there to be 5 exceptions because 5% of 100 is 5. We can then compare that to the actual number of exceptions that we get. So there's 2 questions you could ask. Is our value at risk too high, too low, or is it at the right value? So we put this in terms of a hypothesis test by having the null hypothesis being the probability of an exception is alpha, and the alternative hypothesis is the probability of an exception is greater than alpha or less than alpha. To find those probabilities, you'll have to use the binomial model. From the properties of the binomial distribution, we have a way of actually calculating the probabilities. We just add up all the probabilities that we're looking at. So let's say we have 100 trials. We're looking at an alpha of 5%. And we see that we get 8 exceptions. Then what we want to calculate, what's the probability of seeing 8 or more exceptions, given that our P is 0.05? Well, you calculate the probability of finding 8 exceptions, plus the probability of 9 exceptions, plus the probability of 10 exceptions, all the way up to the probability of 100 exceptions, and add those all up. It's actually easier in that case to do 1 minus the probability of having less than 8 exceptions, which we did with the binomial distribution in Excel. You then get a probability or a p-value, and we will compare this. The standard for hypothesis testing is to use a 95% significance level. And so in this first case, where we see that we get 8 exceptions when we were expecting 6. Getting 9 exceptions when we expect 6. That probability is 15%. It's low, but it's not so low that we would say that this is impossible or not likely. It's not reached that level where we say this is not likely given our data. So that means we do not reject the null hypothesis. But if we have 12 exceptions, that would break this barrier. Our probability would be less than 5%. And so we would say that our value at risk calculation is not right because we have too many exceptions. The other way to test this is to see if you have too few exceptions. That is something that can be tested. However, it is not applicable to Basel because we only care if we have too many exceptions, not too few exceptions. So you could look at this, but it's not going to be, this particular example is not going to be on the exam where you test too few exceptions. All right. Any questions about value at risk or expected shortfall? Then let's move on to chapter 15, which is the introduction of the Basel Accords. What I want you to know about background information is that before 1988, there were regulations in place for how much reserves a bank needs to hold. However, they set those levels based off of the total assets. So it made no distinction between a very risky bank and a very carefully managed bank. And so regulators saw this as a problem and wanted to adjust the capital required so that it would introduce credit risk. So the important thing about Basel I is that it was the first step in attempting to create this international regulation. And the first thing that was tackled was credit risk. The risk that is associated with one party in a transaction not fulfilling their obligations. So, what was done was that in Basel I, there were 3 categories to consider. The first one was credit risk arising from on-balance sheet assets. And what you would do here is just take your total principal and multiply it by a risk weight, which is given in this table here. As an example, let's say you have 100 million of corporate loans, 10 million of OECD government bonds, and 50 million of residential mortgages. Your total credit equivalent amount is 125 million because it corresponds to a 100% risk rate for the 100 of corporate loans. There's a 0 weight for government bonds, and there's a 50% weight for residential mortgages. I did include this thing for corporate loans. That doesn't involve the next category, because the next category deals with off-balance sheet items. Question here.
So in the exam, are we supposed to represent this?
On the exam, I will provide these tables for risk weights. You do not need to write out the tables because, yeah, that's not really helpful information. But what I do want you to notice is the general trend with these tables. The more risky something is, the higher its risk weight, which should make sense with what we're doing here. So things like cash, government bonds, treasury bonds, insured mortgages, they have 0 risk weight. They seem to be risk-free. While uninsured residential mortgage loans or corporate loans can have a higher risk weight because there is a, it's not risk-free, there's a possibility that these transactions are defaulted on. The second category is items arriving from off-balance sheet items. So this could include some contracts, but the distinction is not as important to me. What I really care about are these types of questions. Those arriving from over-the-counter derivatives. We have this formula here, the max of V comma 0 plus AL to calculate the credit equivalent amount. So the first term is the value of this instrument. So let's say you have an interest rate swap that's currently worth 2 million to you. If the counterparty defaults on it, you're out $2 million. However, if you have this contract and it's worth negative $2 million to you, then if you default, you're pretty much saving $2 million. And so that's why we have a max of V and 0 here, because we have to be insured if this has a positive value. or at least that's the credit risk we're exposed to. We're not exposed to credit risk if we're going to be the ones that are defaulting on the contract. And then the second part is the add-on factor, which applies to all instruments. You take a add-on factor and multiply it by the principal of the contract. So these are all percentages here. And they get applied to the second part. So let's say we have a 100 million interest rate swap with a life of 4 years. That's a current value of 2 million. To write out the entire formula, this would be the max of 2 and 0 plus 0.005 times 100. Which gets us a total credit equivalent amount of 2.5 million. So the way to think about this is that this is how much risky money that an individual has. The capital requirement is that there must be 8% of these risk-weighted assets. So this part here is important. 8% capital equals 8% of risk-weighted assets. There are two components to this. There's tier 1 capital, which is like the best type of capital. This includes equity and other things, but equity is really the important part of it. And there's tier 2 capital, which is all the other capital that the institution can offer up. So 8% of risk-weighted assets have to be it has to be saved as capital. 50% of that required capital has to be tier 1, of which 2% has to be common equity. So we have risk-weighted assets. You take 8% of that. This one here can be tier 2. This one has to be equity. This can be other tier 1. And then equity at the top is 2%. So this is how it's broken down. Half of the equity that you have has to be tier 1, and half of the tier 1 equity has to be, half of the tier 1 capital has to be equity. And this gives us our starting point for what the capital requirements are. So at a baseline, with the Basel Accords, you have a credit risk that gets incorporated into your risk-weighted assets. 8% of your risk-weighted assets has to be held as capital. Half of that capital has to be tier 1. And half of the tier 1 capital has to be common equity. We then discussed, so that's pretty much all of Basel 1. Question here. Yes. Yeah. Risk weighted assets are the same thing as credit equivalent amounts. kind of like the total amount of risky money that you have, and that 8% of that has to be applied. So that's really all there is to Basel 1. The things that I want you to be familiar with are what was happening before Basel 1 and how did Basel 1 start international regulations. They started by trying to tackle credit risk. After Basel 1 came out, there were some changes that were made in an amendment. And the first amendment that we talked about was the netting amendment. Netting refers to a clause in an agreement that says all transactions between two parties have to be considered together when default enters the picture. Meaning you can't default on all your liabilities that you owe and not default on all the possible gains you could have gotten from other contracts. So we have an example here where we have 3 transactions that are worth 24 million, negative 17 million, and 8 million. Without netting, you could just default on the trades that are less beneficial to you. With the netting requirement, the bank would have to give up the $17 million that they are owed in one of their transactions. And so it makes a difference between the netting agreement means that the loss is 15 million, while without the netting agreement, the counterparty would lose 32 million. This has the effect of reducing credit risk. It reduces the principal that someone can default on. Question back there. Right. Yep. Right. Yep. So, okay. I might have made this. I might have not been clear with how I explained it. So the bank has transactions that are worth 24 million, 8 million. They're concerned that the counterparty is going to default on that. And so they wouldn't get that 32 million. But with netting, they're a little bit more protected. Instead of possibly losing 32 million, they're only going to lose at most $15 million. So they prefer the second scenario where there is netting because they are protected. The counterparty does not like netting because it means that they aren't able to hold on to that 17 million. So in the first case, our bank, the bank that we care about, loses an extra 17 million because they still have that transaction that they have to pay for. Well, in the second case, if they lose these transactions that are worth 24 and 8 million, then they also get forgiven that $17 million debt. Or that at least is applied to the other debts. So it's a little bit confusing because this is $24 million that the bank is owed. And so you think that that's money that they have in their pocket, but no. Because we're dealing with credit risk here, there's a possibility that the bank doesn't get paid that $32 million. So that's where the credit risk is coming in. Does that make it more clear? It's cool. So netting reduces the credit risk because it reduces the principal. Another way to put this is that instead of having an option on each transaction, you instead have an option on the portfolio of options. So it's all or nothing here. This leads us to the development of the net replacement ratio, which is the ratio between exposure with netting divided by the exposure without netting. This is always going to be between 0 and 100%. And then we calculate the credit equivalent amount. It'll be the maximum of this portfolio value, comma 0, plus 0.4 plus 0.6 times the net replacement ratio times all those add-on factors. And so once again, we can break apart this into two parts. The first term says, okay, if you are owed money in net, then that's money that is at risk. While if you owe money, that's not money that's at risk, per se. If that sum was negative. And so credit risk does not have to be applied to that. The second part reduces the add-on factor, which applies to every instrument no matter what. And if you have a 0% for your net replacement ratio, then your add-on factors are reduced to 40%. If you have a net replacement ratio of 100%, which means netting doesn't give any benefits to you, then the credit equivalent amount is the same as before. So let's think about the case where your net replacement ratio would be 0. That would mean you are in more debt than you have possible gains. And so your net replacement ratio is 0. The reason why that matters is because in aggregate, most of your contracts are ending up costing you money. And so you don't need to add another fee on top of that for the credit risk. So we talked about an example here of what the result would be with and without netting. And so with netting, we have an exposure of 65. Without netting, you would have a fee of 110. Wait, sorry, 125. The add-on is 110 million. Okay, our net replacement ratio equals 65 over 125, which equals 52%. And so our credit equivalent amount equals 65 plus 0.4 plus 0.6 times 0.52 times this add-on amount, 110. So these are the credit equivalent amounts. You would then take that credit equivalent amount and multiply by a 8% to get you your capital. The 1996 amendment also introduced a charge for market risk. So we started off with credit risk. Another type of risk that was important to be added to the next part was market risk, the risk that's associated with downturns in the market. And this is also where we start to see different approaches for calculating your reserves. So the first thing for a market risk charge is to use the value at risk measure. What we have here is an important formula. The charge is the maximum of the value at risk for the previous day, comma, this multiplicative factor times the average value at risk. We talked about MC being greater than or equal to 3, where MC is determined by the number of exceptions that were calculated. There is then also a specific risk charge that is added on top of that. And so what I want you to know about this formula is that the first term is usually determined by the average value at risk. Unless your current losses are 3 times larger than the average, it is more likely that 3 times the average value at risk is going to be what the capital charge is based off of. We also see that we have a 10-day time horizon. So you'll have to include a square root of 10 if you see any questions that use 1-day time horizons. And we have a 99% confidence level. Yes, question here. The value at risk average is based over the past 60 days, while the first value at risk is over a 10-day period. The specific risk charge is a component to this, but we're not going to use any calculations to find it. You should just know that it exists. And then the total capital required was to take this 8% of both the credit risk, risk-weighted assets, and of the market risk, risk-weighted assets. So we use the same 8% for both of them. But one thing to note is that in this example here, this is the capital required. If you multiply the capital times 12.5, you get the market risk-weighted assets. So a distinction here is that we do not calculate the total risk-weighted assets for market risk. Instead, we just calculate directly the capital that's required. But if you want to know what the risk-weighted assets are for market risk, you're going to multiply the capital requirement by 12.5%. That corresponds to 8% of the risk-weighted assets as capital. So you can think about this as 8% the credit risk-weighted assets plus that maximum of the VAR average times 3 plus the specific risk charge. So those are components of the Basel I amendment. There was continued work trying to improve Basel I, and that turned into Basel II, which unfortunately came out right before the housing market collapse. And so it had to be quickly amended afterwards. But it was implemented in 2007, and there were 3 pillars to Basel III. New minimum capital requirements for credit and operational risk, while the market risk is the same as with the amendment. Supervisory review, which is less about putting capital aside, more about having good risk management practices. And then lastly, there was market discipline, which is about disclosures, so that investors can know what techniques companies are using to manage risk. And so that investors can be more aware of the risk that a certain company has. So the new capital requirements include new risk weights based on credit ratings, recognition of credit risk mitigants, and a separate capital charge for operational risk. So the first part describes new risk weights. The second part includes amendments that allow you to reduce the total amount that you have to put in reserves if you have things like collateral. And last part, operational risk, is just a separate charge. So as an example, here's what the risk weights are for banks and corporations under Basel II. Note the difference here. One difference is that there's a lot more options. Another difference is that it takes credit ratings into consideration. So it does not consider all corporate loans to be the same. As an example. Right? Okay, there's also new developments in Basel II that refer back to credit risk, and they involve the probabilities of default. So we have an internal approach. I should say that this is for the internal approach. Remember that for the Basel II and onward, there are standard approaches for calculating charges, and then there are internal approaches. So this describes an internal approach. However, I'm not going to ask any specific questions about the internal approach because I don't think that they're that intuitive. The main thing, though, that you should know is the idea that the probability of default changes depending on how the market is going. So if, in this case, WCDR stands for the worst case default rate, which is the rate of default if the market is in a bad condition. The row here represents the correlation between your investment and the market. And so it denotes how related, if the investment is related to the market and the market is going down, your investment is going to have a higher risk of default. So that's the first pillar. The second pillar for supervisory review changes talks about the sort of standard that should be set across for all risk management departments. We talked about some of these suggestions. I don't think these suggestions are anything extraordinary. And I don't need you to memorize them. The next part is about market disclosures, market discipline, which is about trying to make everyone in the market act relatively safely. So banks will be required to disclose the scope and application of Basel framework, the nature of the capital they hold, the regulatory capital requirements, and the nature of the institution's risk exposure. So this increase in disclosure is important in order to make sure that there aren't big surprises that happen. It's kind of ironic that happened right in 2007 because everyone got hit by a big surprise that year. With the housing market collapse, a lot of these ideas were revised in what is called Basel 2.5. So Basel 2.5 introduced these three main ideas. The stress bar for market risk, that is the value at risk considering stressed conditions, which was what happened during 2007. And it was used because there was very low volatility before the crash. And so a lot of these values at risk were artificially very low. The point of this charge is to be able to survive under stress conditions, so they included that into the capital requirement. This effectively doubles the capital required for market risk. It actually more than doubles it. The incremental risk charge was used to ensure that products such as bond and credit derivatives had the same charge as if in the trading book as they would in the banking book, which we discussed also with Basel III. And then there was a comprehensive risk measure, which had to do with credit-dependent instruments, things like an ABS or a CDO. So as an example of the comprehensive risk charge, you can think of a securitization as an ABS. That's just when you take a mortgage, package them all together, and then sell it to investors. And then a re-securitization is when you take those ABSs and create a security out of those ABSs. So that is, for example, like a collateralized debt obligation on asset-backed security. And you have these percentages attached to them. So those are the three main changes with Basel 2.5. And then we finally get to Basel III, which were the big changes that were meant to address a lot of the issues with the credit crisis. So there are 6 components to Basel III, and I do want you to know all these components. The first component was redefining capital and requirements. Second part was a capital conservation buffer. The third is a counter-cyclical buffer. The fourth is minimum or maximum leverage ratios. Then there are minimum liquidity ratios. And lastly, there's counterparty credit risk. Let's go through all of these. Under Basel III, they redefined what tier 1, tier 2, and equity is, and they redefined the percentages that are required. So in Basel III, common equity had to be 4.5% of risk-weighted assets. That's up from 2% in Basel I. This is because they wanted to have a more set aside for credit risk, and common equity is the best type of way to absorb losses. We require tier 1 to be at least 6% of risk-weighted assets, up from 4% in Basel I. And then tier 1 plus tier 2 had to be at least 8%. But this is only for the first component. The first component has the same total amount, 8% of the risk-weighted assets. But the other components add extra fees on top of that. So for example, the capital conservation buffer is a buffer that's there to protect against market downturns. And what it requires is that common equity create a greater portion of the capital under good conditions. Under stress conditions, this amount can go down. So we're seeing a little bit of the interaction between credit risk and market risk here. When the market's going well, you want to have more capital being devoted towards credit risk. And when things are going bad, it's harder to get that capital, but you have some saved up that you can use. The countercyclical buffer is used to protect against yearly fluctuations in the market. And the key point here is that if these buffers are not satisfied, the government can come in and restrict your dividends. Because dividends are a way for companies to give out some income to their stockholders. But if that income should be used to create reserves, the government's going to make you do that instead. We then discuss leverage ratios, which talk about how much you can do risk weighting. And the main idea is that you cannot apply so much risk weighting that your capital divided by your total exposure is too low. So this compares risk-weighted assets to total exposure. And it says that even if your exposure is not risky, you need a certain percentage of it as capital. So when you're looking at total exposure, you don't do any risk weights. Next are liquidity risk ratios, which were one of the big problems with the credit crisis, the housing market collapse. It was very hard to convert a lot of these instruments into their full value, partially because there was sort of a run on all these instruments. Everyone was selling them all at once, and that drove the price way down. So people lost a lot of money, and corporations were no longer able to fund their liabilities. So we have two ratios that need to be met. The liquidity coverage ratio, which is high quality liquid assets divided by net cash outflows for 30 days. And this pretty much says that you must have enough high quality assets to cover all your cash outflows for the next month. So this ratio has to be above 100%. For the net stable funding ratio, you want to look at the amount of funding, stable funding you need, and compare that to the amount of stable funding that you have. And those factors are found by applying particular either the amount of stable funding factor or the required amount of stable funding factor. So here's an example of calculating the net stable funding ratio. If I was to give you this on the exam, I would provide the table of these factors so you don't have to have them written down on your formula sheet. In this case, we did an example where this ratio is less than 100%. And so more of your assets had to be put into tier 1 capital, as an example. The last component of Basel III has to do with capital for counter credit value adjustments. Or actually, sorry, this is not the last part, but this is adjustments for credit mitigants, meaning that if you have collateral, you can reduce that amount from your risk-weighted assets. And then there is one more for counterparty risk, but I don't think I included here. Another idea that came about in Basel III was the introduction of globally systematically important banks, pretty much saying that the Basel Committee looks at certain banks and says, you are too important to fail, so you have extra regulations that are required. That usually just means something like a 1% or 2% increase in the tier 1 equity that's required. Okay, so that's the end of Basel III. Next, we'll talk about the fundamental review of the trading book. So the main idea is that instead of using value at risk, we'll be using expected shortfall at a slightly lower confidence level. And we have 3 components: a risk charge, a weighted risk charge, a default risk charge, and a residual risk add-on. The weighted risk charge has 3 components: a delta, vega, and gamma component. Where the delta and vegas components are calculated by considering their interactions and their covariance between different risk sectors. And then there was a curvature charge that was applied. This was specifically done by subtracting off the weight for the ith risk from the portfolio and seeing how the portfolio value changes. Comparing the actual change to the linear approximation that would be done with just the delta component. If your actual portfolio value goes down by more than you expect, then that excess has to be included. We talked about default risk charge. There's not going to be any particular calculations with them, and same thing with the residual risk add-on. The last thing that I have here is liquidity adjusted expected shortfall. So remember how in the fundamental review of the trading book, a lot of asset categories were split up into different liquidity horizons. And the last thing here is the distinction between the banking book and the trading book. The trading book has market risk because you want to trade these instruments, while the banking book has credit risk because you're holding these expecting to get a payout from the counterpart. Okay, that's all the time that I have for today. So if you have any questions, please let me know. Remember that we have an exam on Monday, and remember that there's homework due tonight, and the exam 1 makeup is due on Friday. If you have any questions, then please let me know. If not, I will see everyone for the exam next week. Hey.
So
You can come over here if you want. You wanted to look at a specific example?
yeah, like